Hi, this is our first video on numerical summaries, which is going to cover sections 3.1 and 3.2 from your textbook. So first of all, when we're looking at the distribution of data, we really want to consider three characteristics. First is the shape. We already talked about how visualizing the data back in chapter 2 can help us determine whether we have symmetrical data or skewed data. But the numerical summaries, we typically want to talk about the center, right? What would be the center point of our data? And there are multiple ways we can characterize that. And then the spread of our data. Once we know the center, how is the rest of the data spread out around the middle? And that's what we're going to be looking at in these videos. First of all, the center of our data, there are many different ways we can find the center, but we're going to focus on the most popular three in our class. The first one being the mean of the data, which is really just another word for the average, or the median of our data, which really means the middle point, and then the mode. And the mode is the one that shows up the most often. Now, with any time we're doing statistics, we need to make sure that we clearly define the purpose of our study first, because when we describe things like the center of our data, it's going to depend upon how we actually set up our study or our experiment in the beginning. So for example, here are the high temperatures for the first week in May. All right, and we can see that we started with 66 degrees and so on. So again, what's going to be important is defining what our study is actually covering first. Now, if our study is only about the first week in May, then our data set is the population because we have all of the data. And again, understanding the difference between population and sample is going to be kind of important here in the beginnings of our numerical summaries. Now, however, if our study was about the entire month of May, well, clearly I don't have the data for the entire month of May. That means I only have a small sample of that data, which means, well, I'm going to be looking at part of the data to try to determine something about what's going on as a whole. I'm using 1 week in May to try to determine what's going on in the entire month of May. Now our notation. Now again, because our study might have different, depth to it, we need to use different symbols to denote the mean, even though we find the mean the same way no matter what our data is. But it's going to be important that we are on the same page with the correct notation as we continue on through our study. So if I do have the entire population, if I have all of the data, then the mean is going to be given by mu, which is a Greek letter. And well, it's that symbol right there. It kind of looks like a U with an extra line drawn down, or again, kind of an M, I suppose. Now, if I only have a sample, our sample is going to be given by x bar, which is x with a line over it. Now again, they're both means, right? They're both averages, but depending on whether we have the population or the sample is going to make a big difference with the notation and sometimes even the formulas that we use. Now, typically, you're going to see this pattern repeat, where if we are dealing with a population, we use Greek letters, and if we're dealing with a sample, we use Roman letters, which is, again, our typical alphabet, right? Like the letter X. Now, if we're talking about the size of a population, again, if we have all the data, then our population is typically given by capital N. But if we just have a sample, then the size of our data is given by little n. We're also going to see this symbol show up. This is the Greek letter sigma. It is a capital sigma. And it is basically the Greek letter for S, and it means summation. It means add it all up. And again, you're going to see that Greek letter capital sigma show up a bunch of places because it's just very convenient notation to say, all right, add everything together. Now, when we're talking about our data points, again, typically our data points are given by x's, but we have lots of data points and lots of different x's, so we do a little subscript. And our generic data point is x sub I. But when we actually go through and do the data, we'll have x sub 1, x sub 2, x sub 3. And again, I being just kind of a counting variable that we use as more of a placeholder than anything else. So let's go back to our example about those temperatures. So let's say our study is about just the first week in May, which means we have the population, and we want to know what the average or the mean temperature was for that first week in May. Well, the way we find that is going to be this formula here. which, again, it looks intimidating, but it is in fact incredibly easy, because all this is saying is that mu, or my mean, is equal to, well, on the top, it's that summation. So add up all of the x sub I. Just add up all the data points. And then divide by n, which is our sample size, divide by the number of data points. And I'm guessing most of you probably already know how to find averages. You already know that you add it up and you divide by how many you have. This isn't anything new, but again, it's this notation that, well, can sometimes make it way more difficult than it actually is. Because, well, it is important to have a set of language that we can use to describe things. But there's also, well, a more sinister aspect to it too, and that's if I tell you that I'm using this formula and you have no idea what it actually means, well, you might be inclined to think that I am much more of an expert in this field than is necessarily true. And I mean, we see that everywhere, right? Mechanics use the proper terminology for a car, which is necessary for their jobs, but that doesn't necessarily mean that we always know what they're talking about. And if we don't know what they're talking about and we're uninformed, well, they might be able to take advantage of me being uninformed and charge me a lot more to repair something because I'm ignorant about what's actually going on. And mathematicians use that too. And banks use that, right? When they start spouting out lingo like prime rate derivatives and this, that, and the other thing. That can be intimidating if you don't know what they're actually talking about. But again, if you can demystify what's going on, you'll see that in reality, nothing is typically as hard as it actually seems. But let's get back to the mathematics. Again, that's my notation. And like I said, it's really easy. You probably already know how to find averages. You add up all the data values and divide by how many. So if we had a week's worth of data, add up all the temperatures, divide by 7, we get 60. The average, or the mean temperature for the first week in May, was 60 degrees. That's it. Now, note, this is a parameter. Remember, parameters mean that we have all of the information necessary, and parameters describe our population, right? The P and the P. Population parameter, population parameter. Now let's say that again we have that same set of data, but now I want to make a statement about the month of May, the entire month of May. But again, remember, I only have a small sample. I only have 1 week of data to describe the entire month of May. And I now want to find what the average of the mean temperature is. Well, here's the formula. X bar equals, well, the summation of all the data points over n. Now again, we use lowercase n now because it is just a sample. But it's the same thing. Add up all the data points and divide by the number of data points. And as you can see, if we do that, nothing has changed. We're still going to get the same average. We still get the same value. All right. The only difference is now it's x bar instead of mu, but that's it. And now my summary would say that the mean temperature for the month of May was 60 degrees. And again, I'm still making that assertion even though I'm missing data. And you're going to see that that's basically how almost every study is done. And we're going to look at ways that once we get to probability, how we can maybe manipulate that sentence to be a little bit more accurate and actually include the fact that, well, we didn't really use every single day in May. We only used this first week. Now again, because we're missing the data, because we just have a sample, that means that this is a statistic. All right. I made this claim based on limited data, which means that this now is a statistic. The mean temperature for the month of May was 60 degrees is a statistic. So I'd like to take this chance to kind of update our definition a little bit. And again, if you read through chapter 1, you saw that statistics was the science, and again, I like to call it an art too. So it's the science or the art of collecting, organizing, summarizing, and analyzing information when some information is missing. Again, statistics is when that information is missing. All right, next set of definitions, we're talking about the median. So the median is the middle of a set of data arranged in order. So basically the median is just arrange your data in order and then find out what's that middle point. All right. Now, for the median, we use capital M, and there's no distinction whether it's a population or a sample, which means there's no distinction between whether we're talking about a statistic or a parameter here. M is just M. Now, if there is no middle value, if there's an even number of data points, well, then we're just average the two middle values to find the median. And we'll see examples in these two videos on chapter 3 of both ways. But going back to our example, if I want to find the median temperature for the first week in May, well, again, I have all my data, but it's unordered, right? There's no order to it. So the first step is to order it. Put the smallest value first up to the biggest. And so I did that. And now all we do is look for, well, what's the data point in the very, very middle? And that's clearly going to be 57. There's 3 to the left, 3 to the right. What's in the middle? 57, which means the middle of the data is 57 degrees, or the median temperature is 57 degrees. And so again, we saw that the mean temperature was 60, but the median was 57 degrees, which means depending on which center I decide to use, and both are valid. We can use the mean and we can use the median. Using 2 completely valid centers, we came up with, well, 2 different temperatures. And you're going to see, again, if you watch the video on deceptive statistics, that happens quite a bit. And determining which would be the better center to use, what would be the better descriptor, is kind of an important skill. And it's going to depend on the shape of the graph. And we're going to talk about that a little bit more later on. Now, the last center we're going to look at is the mode. And mode simply means it's the value that shows up the most frequently. Now, sometimes you'll look at a data set and nothing shows up the most times, which means there is no mode. Also, sometimes you'll look at a set of data and 2 data values appear the most. In this case, the data is bimodal, and both of those values would be our mode. Sometimes even 3 or more data values appear the most, and then we say the data is multimodal, although when lots of data values start showing up with the same frequency, you start, again, getting into that gray area. Well, is it multimodal or is there really no mode because nothing's really showing up the most? And again, there's a little bit of ambiguity and a little bit of art to statistics there. Now, the mode is very, very nice because I can use the mode to actually describe qualitative data. Now, those temperatures were quantitative. They were quantities. They were numbers, right? The temperature is given as a number, and I can arrange those in order, and I can average those. But with qualitative data, I can't really order it. And again, if you watch that first video when we talked about the color of cars, well, there's no way to really rank the colors of cars. You know, which comes first? Does red come first, or silver, or so on? But with qualitative data, the mode can be used. What color car shows up the most? And that becomes our center, because that shows up the most. Now again, looking at our data set, if I wanted to find the mode temperature for the first week in May, we just want to look for the one that shows up the most often. And in this case, we see that, well, it looks like 57 degrees shows up twice, so the mode of our data is 57 degrees. Everything else shows up once, 57 shows up twice, so the mode is 57. It's what shows up the most. Now, like I said, depending on the shape of the data is going to tell us, well, which center would make more sense, and it actually tells us a little bit how the numerical summaries are related to our data. So what's going to happen is that if we have data that is skewed, meaning that it's either skewed left and there's more data points to the left-hand side of our peak, or skewed right and there's more data points to the right-hand side of our peak, that skewedness, that data out towards those tails pulls the mean in the direction, which means the mean is no longer really the most accurate way to describe the data. Skewed data pulls that mean to the side, but it doesn't pull the median. And so if we have skewed data, what we should do is use the median as our center. Anytime we have skewed data, the median becomes the much better descriptor of the center of our data. Now, if our data is symmetric, if we have that bell-shaped, well, then the mean and the median are equal to each other, and typically we're going to use the mean because, as you see as we go through, we talk about the next topic, which is dispersion, it's much better to talk about the mean in terms of dispersion than necessarily the median. Now, you'll also see with that symmetric data, if the mean and the median are the same, remember that mode is also the one that shows up the most frequently, and clearly that peak, right, in the center, when we're talking about our symmetric data here, the mean and the median are the same, and it's also the same as the mode. And they're all going to be the same. All right, and like I said, we can also look at mathematically. I can usually tell the shape of the data without necessarily having to graph it, because again, if my mean is smaller than my median, typically we're going to be skewed left. And if my mean is bigger than my median, it's skewed right. And again, this is kind of a nice little cheat sheet to help us figure out, well, what is the shape of the data? And gives us a numerical way to look at it. But let's talk about dispersion now. Now, dispersion means the degree at which the data is spread out. And so sometimes we say dispersion, or what's the spread of the data? How does the rest of the data look besides just the center? The first way we can talk about how the data is spread out is with the range. And the range is simply, well, what's the difference between the largest and the smallest data values, right? What is the range of the data? How far do they go in either direction? So, like I said, range, we use the letter capital R, and we just subtract those two data values. Deviation is going to be a measure of how far away a data point is from its center. All right, so deviation is how far a data point is from the center. Typically, again, if we have symmetrical data, we're going to talk about the deviation from the mean. Now, the deviation from the mean is, well, how far is a single data value from the mean? Take that data value and subtract what the mean is. How far away are they? Standard deviation is how we measure the deviation from the mean, but for all of the data points in a set. So again, deviation about the mean is, again, to talk about a single data value. The standard deviation lets us talk about the entire set of data. So let's go through and talk about these dispersion techniques. First, find the range of temperatures for the first week in May. Like I said, you just look at the data set. What's the biggest one? What's the smallest one? Subtract the two, find their difference. So the highest temperature was 68. The smallest temperature was 51. When you subtract those two, we get 17. So the range of temperatures for the first week in May was 17 degrees. Hopefully that's fairly straightforward. But now let's say I want to find the standard deviation for the first week of temperatures in May. Well, first of all, I'm going to do this by hand because it's really important to understand where the standard deviation comes from and how we actually find it. However, in practice, you should almost always use technology to find the standard deviation. And again, I'll talk about how to use technology a little bit later in other videos and other handouts. And again, the notation is going to matter quite a bit when we're talking about, well, samples versus populations. But for now, let's just go about finding that standard deviation for the first week of temperatures in May. Now, what we really want to do and what's going on is that we list all of our data and we find those individual deviations from the mean. So remember, the deviation from the mean is that data point minus the mean, and again, it helps us with the individual data points. So we knew that from earlier that mu was equal to 60, right? That was my average temperature. And so when I take my first data value, 66, and I subtract it from 60, that result is, well, 6. It was 6 degrees off of the average. And I can go through and do that with the other ones, right? 68 minus 8 and so on. Now notice though, when I get to something like 57, well, 57 is smaller than my mean. 57 is smaller than average, which means that deviation is actually going to be negative. All right, which is very useful. It tells me that individual data point is smaller than the mean. So again, that negative helps out quite a bit here. Now, when we're trying to find the standard deviation, again, all these individual deviations from the mean are very useful for those individual data points. But notice when I sum those all up, and again, feel free to check on your calculator and pause the video, it's always going to sum to 0. Because this is why the mean is that center of the data, right? Every data value is centered around it. So when you sum up those deviations from the mean, how far is each data value away, they all need to kind of cancel out to get us back to the center of our data. So how do we deal with that? Now, admittedly, there's more than one way to deal with this, but the standard deviation does this by taking the square, right? Or multiplying that number by itself. So again, with that example of 66, we know it's 6 degrees away, which becomes positive. And when I square 6, 6 times 6 is 36. It's still positive. When we looked at 57, again, that difference from the mean was -3 because it's smaller than average. But when I square it, -3 times -3 gives me +9. And now all my deviations from the mean have now become positive because I squared them. And now when I sum them up, I get 284, which is actually a useful number. And again, feel free to pause and check my math, but I'm pretty sure I did this right. So now that we have that value, we want to find the average of those squares. The average of the squares is called the variance. And so our formula for the population variance is, well, this. And again, it looks more mystifying than it probably is. But essentially what it's saying is find those differences, right? Subtract those two, square them to make it positive, and then it's the average. Add them up and divide by the number of data points. So when I add those up, I got 284 divided by 7, so that gives me roughly 40.571. And again, it's not going to typically work out to nice, neat numbers, right? In statistics, it's almost always going to be decimal, so just make sure you're paying very close attention to how many decimal places the problem is asking you to actually write out. Now, here's the thing, though. I squared those differences to make it positive, which means my units now are degrees squared. So if I said the variance is 40 degrees squared, okay, well, that's not particularly useful, right? Because we want this in terms of just kind of degrees and temperatures. So all we want to do now is take the square root, right? I squared it once, so now I got to take that square root, and that'll give us our standard deviation. And so, again, the standard deviation is always just the square root of variance. And so, in this case, the square root of 40.571 is approximately 6.37. So the standard deviation for the high temperature for the first week in May is 6.37 degrees. Now notice, I am pretending like I have all of the data, right? This is the population variance. I'm only talking about the first week in May, and I was able to find that standard deviation. And again, see how that standard deviation kind of compares to my original data set. All right, when I look at all those different deviations, well, again, it varied, positive and negative. And so, well, yeah, about 6 degrees or so was, on a kind of how far, gives us kind of an average of how far away from the mean of 60 degrees a lot of those data points were. Now our notation. The population standard deviation is the Greek lowercase sigma, right? Standard deviation, S, the Greek letter S, sigma for standard deviation. Now, because we took the square root of variance, we're just doing that in kind of the reverse order now, right? Square roots are the opposite of squares. So the population variance is going to be sigma squared. And when we have samples, we just use the Roman or our typical alphabet, S. So S is our sample standard deviation, which means S squared is our sample variance. Now, when we calculate the sample variance, we actually have to calculate this slightly differently. This is where the difference between populations and samples really starts to come into play. With the sample variance, I actually divide by n minus 1. I'm not dividing by the total number of data points. I'm actually dividing by 1 less than that. All right, which means the sample variance is always going to be bigger than the population variance. This is because, well, when we take a sample, we're missing some information. And so typically, if I had all the information, if I had more data points, we would assume that those more data points are actually going to be more spread out than the small little sample that we have. Typically, again, this is kind of a typical thing. Typically, if we have just a small sample, probabilistically, right, that small set is going to be closer together than the data set as a whole. So this is how we correct for this. This is actually called the Bessel correction, and this is one of those things where he was actually doing the math and his numbers were coming out incorrect, and he realized that if you have a small sample, well, you need to make this little correction to make sure it matches the population. All right. Now that n minus 1, and you're going to see this, it comes up again later on when we're doing probability and the inferential statistics later on. N minus 1 is what's called the degree of freedom. And you can kind of think about this as, let's say we were actually in a classroom that had 24 chairs and 24 students. Well, the first student could choose any chair he wanted, right? But the second student through the door isn't going to be able to choose any desk they want. They have to choose, well, they have one fewer choice. And that's kind of what degree of freedom means. Now, this is a case of bias. If I have a small sample, my small sample is not actually going to represent what's going on with the entire population. And so the bias needs to be removed. And that is, again, dividing by n minus 1 instead of just n. Now, again, if you read chapter 1, bias comes in a bunch of different kind of categories where, there's just regular bias, there's sample bias, non-response bias, response bias. But bias can also find its way creeping into the actual mathematics, and we need to make sure that we take care of that too. Now, like I said, typically you want to use technology to calculate these things. You don't want to do it by hand, but it is a good idea to understand what's going on and why those numbers are going to be different when we use technology. So, going back to the example, let's say I wanted to find the standard deviation temperature for the entire month of May. Well, remember, it's the entire month, but I don't have the entire month's worth of data. Now, I still would go through the same steps, the same way we did before to calculate the variance, up until we divided. So again, I would still find those individual distances from the mean. I would still square them. I'd still sum them. I'm still getting that same value. Again, 284. That part didn't change. The only thing that changed now is I'm dividing by 6 instead of 7. And so that's going to give me approximately 47.33 in this case. So there's my sample variance. And the same idea as before, the standard deviation is the square root there. So even the sample standard deviation means taking the square root of the sample variance. So take the square root of 47.33. Now we get approximately 6.88. So the standard deviation for the high temperatures for the entire month of May is 6.88. And again, notice that this is bigger than just the first week. And hopefully this makes sense too, that if I was looking at the entire month of May, we would expect there to be more variance, right? We would expect there to be more dispersion, more spread. We would expect those temperatures to be far different if we looked at the entire month of May as opposed to just one little week. Now, in general, the more spread out the data are, the greater the standard deviation. That's what the standard deviation measures, how spread out those data values are. So if the standard deviation was 0, that means there is no deviation. There's no variance. It means that every observation is exactly the same. Right? If my data set was the numbers 20, 20, 20, 20, 20, 20, then there is no deviation. Everything's the same. The standard deviation would be 0. And again, that's kind of the intuition behind what that standard deviation is telling us. Now, like I said, in practice, you're never going to calculate a standard deviation by hand. There's no point writing out that entire table like I did. I just really wanted to show you what we're actually calculating so you have an intuitive idea behind what's going on. Now, when you use that technology, you got to make sure that you're using the technology the correct way. If you find these values, if you find standard deviations and variances on your calculator, your TI-83 and 84, they make the distinction between the population and the sample using that notation. Is it a sigma or is it an S? And when you're calculating one variable statistics, and I'm going to send you a separate handout on instructions on how to do that, it'll be right there. It's going to give you a giant list. It'll give you the population standard deviation and the sample standard deviation in the same list, and you just look at that notation to figure out which one you need. If you're using Microsoft Excel, again, you're typing these formulas in. You need to be very explicit about what it is you're doing. And so for the standard deviations, the way they distinguish them on Microsoft Excel is typically either stdev.p for population or a .s at the end for sample. And again, I'm going to do an entirely separate video on the Microsoft Excel functions or formulas on how to calculate those. But I want to talk about the empirical rule now. And again, how the mean and the standard deviation are related to each other. And this is the special case when we have data that's bell-shaped, right? That's symmetrical bell-shaped, meaning that the data is unimodal and it's symmetric about the mean. And like I said a little bit earlier, this is where the mean, the median, and the mode are all equal to each other. And again, if we have data where the mean, the median, and the mode are all equal to each other, we have that one peak in the center and it's symmetric on both sides, it's that bell-shaped, we use the empirical rule. Now, the empirical rule is more of a rule of thumb. It's a generalization that helps us do statistics very, very quickly without necessarily having to do some complicated calculations. And again, it's great for a introduction to statistics course or a first course in statistics. Now, what the empirical rule states is that approximately 68% of the data is going to be within one standard deviation of the mean. All right. So again, mathematically, we have that symmetrical data. If I calculate one standard deviation from the mean on either side, so plus and minus, right? Approximately 68% of that data is going to lie between those first standard deviations. Approximately 95% of the data is going to lie within two standard deviations of the mean. All right, it means, again, approximately 95% of the data is going to be between two standard deviations from the mean. So if you start at the mean in your center and you go two standard deviations to the left, two standard deviations to the right, that should encompass about 95% of your data. Now, typically, when we talk about something that is unusual, again, typically, although this changes depending on what we're looking at, typically anything in the outside 5% of data would be considered unusual. All right, if it happens less than 5% of the time, that's unusual. And so, again, if 95% is in the middle, then the outside 5%, which should be equally distributed, 2.5% in the left tail and the right tail, that becomes our basis for describing something as mathematically unusual. Again, that's a mathematical definition. You're going to see that, again, in mathematics, we have really two choices when we're doing mathematics and we're trying to describe something. We can either come up with an entirely new word like a isomorphic hypergeometric function, which sounds really intimidating, but is very specific in mathematics, but it doesn't really have much of a meaning for most people. Or we can take a word that already exists and give a mathematical meaning behind it. And that's the same as, in this case, unusual. Again, something that's in that outside 5%, we might not typically consider it unusual in our common language, but it is mathematically unusual. And there's a big difference. And you're going to see that happens also when we start talking then more about probability, and we have to define things as successes or failures. And if we're looking at, cancer rates, we might actually denote getting cancer as a success mathematically. That doesn't make sense, of course, in our normal everyday language, but again, mathematically, well, it kind of does, I suppose, because that's how we're going to define it. So again, anything outside that 95% is typically considered unusual, going out those two standard deviations. And the last part of the empirical rule, approximately 99.7%, so that's almost all the data, has to lie within three standard deviations of the mean. So again, that means approximately 99.7% of the data is going to be, if you start at the mean and you go out three deviations to the left, three standard deviations to the right, that's got to be 99.7% of the data. Visually, this is what that empirical rule kind of looks like. And again, you could do a bunch of mathematics here to actually, break it down a little bit more, and you're going to have to do that with your homework. But again, we have the mean in our center, right? There's my mean, mu, although this actually does also work for samples as well, if it was x bar. But we have our mean in the middle here, right? And again, that's the peak, that's the highest point. And if we go out one standard deviation on both sides, right? We go up one standard deviation here to the left, one standard deviation out here to the right. 68% of our data is going to lie there towards the center. If we go out one more standard deviation, if we go out one more standard deviation to two standard deviations, right, we see that now we have 95% of the data. And if we go out one more, we're at 99.7% of the data. So let's do an example to actually kind of look at this and see what this really means in context. So the average height for an adult man in the United States is normally distributed, which means it's symmetric. When I use that phrase normally distributed, that means it's the symmetric or the bell curve. Normally distributed, bell curve, those are actually kind of interchangeable. So the mean is 70 inches. That means that the average man in the United States has a height of 5 foot 10 inches, or 70 inches, and there's a standard deviation of 3 inches. So what does that mean? Well, most men, about 68%, are going to have a height that's within 3 inches, which is one standard deviation of the mean. So my mean is at 70, so if I go out 3 inches on both sides, so 67 to the left, 73 to the right, 68% of men are going to be within that range of one standard deviation on either side. So again, most men would be between 67 which would be 5'7" or 5'7", 5'7", and 73 inches, which would be 6'1". So again, most men are between 5'7" and 6'1". Almost all men, so now we're at the 95%, are going to have a height within 6 inches, and that's 2 standard deviations, right? If one standard deviation is 3 inches, 2 standard deviations would be 6 inches. And again, almost all men would be within, would be about 95%, and would be within that range from 64 to 76. Now again, mathematically, that would mean that any man shorter than 64 inches or taller than 76 inches would be mathematically unusual. Now, is that unusual in real life? No, that's not really unusual in real life. We wouldn't consider someone, a man who's shorter than 64 inches to be unusual. But mathematically, again, that is our distinction, right? That outside 5%. So again, we would expect about 95% of men to have a height between 64 inches or 5'4" and 76 inches, 6'4". And lastly, about 99.7% of the men, again, that's almost 100% of the men, are going to have a height within 9 inches of that standard deviation. So again, that would be between 3 standard deviations. And so again, if we do the math, if we subtract 9 to go to the left, we get 61. Add 9 to the right to get 79. We would again expect that many men to have heights between that particular range. All right. That about wraps it up for 3.1 and 3.2, talking about our centers and our dispersions. We're going to pick this up again in the next video, talking about, well, how do I compare different sets of data?